Now, when you're working in environmental monitoring, very often they will express concentrations in these units. Here you have parts per thousand, parts per million, and parts per billion. Now, these are just like percents. You can think of a percent as parts per hundred. So they're going to work just like percents do. If someone tells you that seawater is 35 parts per thousand salt, you can write that down as 35 parts salt for every 1,000 parts seawater. So it is pretty much just the same thing and works the same way as a percentage, and can do the same kind of things with it. You just have to remember that the T is thousands, parts per thousand. The M is millions. And the B is billions. And these are long enough numbers that you could use powers of 10. So let's do an example. Let's suppose that there is a chemical called methylmercury. It's an ion that looks like this. That's enough to kill you if you get that high a concentration of this in your blood. Now, where does methylmercury come from anyway, as long as we're talking about that? This happens when mercury gets into the environment. And bacteria work on it. They will spot weld a carbon-hydrogen piece onto it. And this makes it very easy for it to get into a living thing, because it can cross a cell membrane and get into cells fairly easy that way. And it will concentrate the higher and higher up in the food chain you get. So you can get this sometimes in dangerous concentrations in fish, where there's been some mercury contamination. Where's the mercury come from? All kinds of different sources. Burning coal is a big one, though. All right, let's suppose that we have this. What does this mean in the first place? It means that you have 1.5 parts of methylmercury per million part, and instead of writing the 1 with the 6 zeros after it, I'm going to write 10 to the 6 parts blood. So it is kind of a conversion factor between an amount of methylmercury and an amount of blood when someone gives you a concentration like that, and you can use this as a conversion factor in calculations. Now remember, the whole thing about percents also applies here. We don't know what parts means necessarily. Depends on whether something is liquid or solid, which is more convenient. When they don't tell us with these, we're going to assume a default. So we'll assume it's W/W. If it really matters, we better be sure we know whether it's WW or WV or VV. You know, that's going to make a difference, especially if you're talking about tiny concentrations of something that's lethal. It makes a difference what parts means exactly here. Anyway, I could put grams in there if it was WW. All right, so this would be a conversion factor between grams of blood and grams of methylmercury. Now, there's a couple of different ways that you can write parts per million here. If you look at this, if I write milligrams per kilogram, there happen to be 1,000,000 milligrams in a kilogram. So I could write this. So you can write down 1.5 parts per million as this, or you could write it as that. That will work. Sometimes people will, when you're talking about water solutions, you can put a volume on the bottom there. And if you have something that's mostly water, nearly all water, you could write this as a kilogram of water is the same thing, weighs about the same thing roughly as a liter. So you could say parts per million was a milligram per liter. Now let's summarize this. 1 part per million is the same thing as 1 milligram per kilogram exactly. When you're talking about water solutions, and the solutions should be fairly dilute, you can say this is about a milligram per liter. So when people are talking about parts per million, it's a milligram per liter. If they're talking about, say, chloride concentrations in water are 15 parts per million, you could say 15 milligrams per liter. And you'd be pretty much okay to 2 or 3 significant figures. But I'm going to say that's approximately true. This is exactly true. This is approximately true. What about a part per billion? Can you do something like this with a part per billion? Sure. 1 part per billion happens to be a microgram per kilogram. Same thing. So if you're talking about weight, W/W, you could write it either as parts per billion or micrograms of solute per kilogram of solution. And if you've got a water solution, you can write this as approximately equal to micrograms of solute per liter of solution. Put a box around this because sometimes you have to move between parts per million and milligrams per kilogram, and this kind of makes it easier to do unit conversions when you've got parts per million. Let's suppose that I have a solution that is, I don't know, 500 parts per million sodium ions. And I want to figure out what the molarity of sodium ions is. Okay. I want to turn that into moles of sodium per liter. Now, it is so much easier if I remember what we were just saying here, that a part per million is milligrams per kilogram. If I put milligrams per kilogram there, that makes it a little easier. I would have to know the density in order to convert kilograms of solution into liters of solution. If it was a dilute aqueous solution, the density is about 1, because that's the density of water. It's about 1 kilogram per liter. So you could just say, if you just wanted to one significant figure, which is looks like maybe all I've got here, you could say instead of 500 parts per million, you could say roughly 500 milligrams of sodium per liter of solution. And then it's even easier for you to turn that into a molarity, see? But there's an approximation here. So you're going to get something that's only going to be good to maybe 2 significant figures, 3 significant figures at the most, because that's all you know the density to. The density is 1 to 2 or 3 figures. All right, so I would have to turn milligrams of sodium into moles to get this done if I was doing this last one. That's not too hard to do. I can turn milligrams of sodium into grams of sodium, right? 1 milligram is 10 to the minus 3 grams of sodium. And then I can turn grams of sodium into moles of sodium, and I'll have it done. So I need the molar mass of sodium. If I look at the periodic table, it's something like 22.99 grams of sodium for 1 mole. So I pick up my calculator now. 500 times 10 to the minus 3, that'll be 0.5. I can do that in my head. 0.5 divided by 23 would be like 1/46. That'd be like something like 0.02 or something. Let's figure it out. 500 times 1 EE minus 3 divided by 22.99 is, 2 times 10 to the minus 2. I am only going to get 1 significant digit off of this. I can write it down either as moles of sodium ions per liter, or I can write it down with the abbreviation for molarity, like that. So these things that I have boxed are nice things to remember when you are in environmental science and you're doing calculations with these concentration measures. These, by the way, are the most common concentration units that you will see in stories about environmental toxins, because usually they will report environmental toxins in these units here.